the learning outcomes under the topic equations of motion. At the moment, we are here at the bottom part of the targets. Describe and explain motion having components like constant velocity in one direction and a uniform acceleration in another. This is also the reason why I decided to give you this. You see, as a start of our discussion. Let's say there is a guy standing on top of a cliff, like what you are seeing on the screen right now. Three identical balls will be thrown by this guy, of course, giving it the same initial speeds, but in different directions. In case A, or ball A, it is thrown upward, B is downward, and C is thrown along the horizontal axis. Now, what we are going to investigate are their speeds and velocities just before they touch the ground, meaning we want the V value at that time like a billionth of a second before each ball hits the ground. Remember this problem, okay? I am erasing it so we can have a space for our working. So here we have the first ball, ball A, thrown upwards, it goes up, then down like that. The second ball, ball B, is thrown directly down like this. For C, we will do that later. These two balls first. Now the motion of ball B is simpler. It is a free fall, meaning that the acceleration here is 9.81 meter per second squared. And we want to know the final velocity or speed if you want to just focus on the magnitude in this case. And our displacement with symbol S, which is supposed to be the straight line distance from this starting point to this end point. With all the variables or quantities we have in this problem, we can pick the fourth kinematic equation with the u as the initial velocity of the ball. And in the end, our working equation will be this. This tells the speed or the magnitude of the velocity of ball B just before it hits the ground. Now for ball A, it is also a free fall. Remember, our definition is that a free fall is the motion of an object influenced by gravity alone. So this one qualifies. Even if it's thrown upwards, the only force acting on it is gravity. The motion of ball A, therefore, is an example of a free fall. It has this acceleration of free fall. We want to find the V, and S is also here, or the displacement. And of course, same initial speed or magnitude of velocity, which is the U. These are all the same as in ball B, meaning the final speed and the final velocity of ball A must be the same as in B. Okay, if you're a bit confused, another way to look at this scenario is to divide the travel path of the object. First division could be this, moving up with decreasing speed, reach the peak, then goes down till it gets back to this same initial location. The other part could be this, from this position where ball B was also thrown downward, down to the point just before it hits the ground. For the first part, the displacement is zero, and that if we are to compare the initial velocity of the ball A to the velocity at this point, when it returns to the same location, we can use this kinematic equation. This. This is zero, the displacement, and we should end up with this relationship. The speed here and the magnitude of the corresponding velocity must be the same compared to the initial one. Since the velocity here has the same magnitude as the initial velocity, this tells us that this part 2 of the path, this one, is the same as what happened in ball B. And therefore, the speed and velocity of ball A just before it hits the ground is the same as the speed and velocity just before ball B hits the ground. This quantity here. Okay, let's clear the screen a bit. Summarize what we found here. Balls A and B, same speed and velocity. Let's move to the third ball C here. It is given the same initial speed, direction is different, see that arrow. The motion can be analyzed by looking into the components of its motion. Here we have constant velocity motion along the x-axis, and along the y or vertical axis we have a uniform or constant acceleration. Let us write that. Constant v here, or uniform velocity along the horizontal, and the component of motion here along the vertical is a free fall. Since v is constant, the acceleration is zero here. Along the vertical, however, we have constant acceleration, or the acceleration due to gravity, or the acceleration of free fall, which is negative 9.81 meter per square second. After some time interval, ball C is probably going to be here. The reason is it is moving at constant v along x while accelerating along the vertical. See that I tried to draw a red arrow of same length as the first red arrow to imply that the speed remains the same. Along y, however, this small green arrow implies that the velocity along y changes, and at the moment it is not that fast. These would give a displacement here along x and a small displacement here along y. Now, after another time interval, ball C could be somewhere here. The displacement along x is likely the same as before if the time interval is just the same as before. Constant speed here, remember? However, the vertical axis, the velocity at this time is a bit faster. This longer green arrow as compared before. Remember that along y-axis, the motion is accelerated. Now, after another regular interval, the displacement along x-axis remains the same as seen by equal spacing, constant velocity along the x-axis. Now, along the vertical, because there is a uniform acceleration, the velocity must have become faster here, the longer green arrow. These changing vector arrows representing velocities at some times explains that there are differences in distances or displacement along the vertical. Along horizontal, the distances or displacement is kind of constant, all right? Now, the overall look of the path of ball C, therefore, is like this. A curve, a path called trajectory. Okay, we are not done yet. Let's copy the diagram and transfer here so we can do further analysis. What we want to know is the speed and velocity at this point, just before it hits the ground. And compare that with that of balls A and B later. Based from the diagram, the velocity here can be represented by a vector arrow. Let us name this as vector v or velocity v, the one that we need as per our question. To emphasize that we have two components of motion in this case, we can draw a triangle here with this side as the component of velocity v along the y-axis, say a free fall component, and the component along x-axis, this one, which is also equal to this. It is a constant velocity. Now let's name this as v subscript y, and this one is v subscript x. Okay, along the vertical, at this point, the component along y is like when you have a free fall. We drop the object, meaning that the initial velocity is zero at first along the vertical. And that using this kinematic equation with this as equal to zero and this one here is the component along the y-axis, we will have this, the vertical component, which is square root of twice the product of acceleration and displacement. Now, for the horizontal component, we have the initial velocity given to the ball, which is u here at this point. Same symbol used in ball A and ball B, which is given in the problem. Since we have a right triangle, we can use the Pythagorean theorem that the v we need to find is equal to the square root of the sum of the square of the components along the x and along the y. From the triangle here, we can substitute the v subscript x, which is u here. And for the vertical component, this one, we take this and here you go. Our expression for the final speed or the magnitude of the final velocity just before it hits the ground. Now it's time for us to compare what we got for ball A and ball B. Remember, they are the same. The ball A and ball B a while ago. Let me show you what we did. This one for both A and B. And for ball C, it is the same, as you can see from the equation here. Given the situation, all balls A, B, and C will have the same speed and magnitude of velocity just before they hit the ground. Also note that in the case of ball C, this is just for the magnitude of velocity and also, of course, the speed. And since velocity is a vector, you need to determine also the direction angle of this vector arrow to accurately describe its velocity. Okay, bye.